Okay, so my name is John Becker. I'm a software engineer at Chainalysis. Um, yeah, you might know me for the Heimdall toolkit. Um, I'm going to do a brief overview of EVM and some internal smart contract design patterns that you might find when you're working with the EVM. So if you know nothing about the EVM, you don't have to worry. I'll teach you a bit about it. So let's get started. So I'm going to start by talking about the anatomy of the EVM. How it handles signatures and selectors, bytecode, opcodes, assembly, program execution, and the control flow graph, internal smart contract design, and then I'll leave you with some helpful tools and resources to continue your research on your own. So to start, this is a nice little graphic from Ethereum.org, which helps give a high-level overview of how the different parts of the EVM come together. So you have the volatile machine state on the left. This is basically just machine state, which will only persist until the end of a transaction, and then it doesn't exist anymore. Don't worry about what these are yet. I'll talk about them in depth later. This is like to give you a little overview of what we're going to talk about. So you have machine state, and then you have the EVM code, which people also call bytecode. That's immutable in most cases. You can sometimes redeploy code to a contract, but not always. And you can also self-destruct contracts, but the code still exists in the state. And then you also have account storage, which persists all the time and is usually used to store things like ERC20 balances, NFT owners, mappings, etc. And all of this encompasses the EVM. Yeah. Now we'll start with the stack because it's like the core of the EVM. The EVM is a stack-based virtual machine with a word size of 256 bits, which just means that the largest integer you can have is like 2 to the power of 256. And then you can only have like bytes up to 32 bytes. Uh, yeah, that's the limitations for the EVM. But honestly, if you think about it, that number is so big, you're never really going to need anything bigger than that to write a program. Like most of your computers right now work off of stacks of like 86 or 64 bits. So
Yeah,
if you think about it, 6 is a lot.
I heard the number is bigger than the amount of atoms in the universe.
Yeah, it's a huge number. Um, so yeah, it's a last in first out stack, which just means the last item you add to the stack will be the first item to come out. And you can kind of see on the left, if you push 0, 1, and 2, you're going to get a stack that looks like that. Yeah, there's a maximum depth of 1024. You'll probably never reach that unless you're doing something weird. But you can only access the top 16 words for technical reasons, which I'll go into later. And this is why you'll get like stack too deep errors with Solidity. Yeah, so let's move on to memory. Memory is used for storing information that might be longer than 256 bits. Despite its name and what you might think, it actually doesn't persist. Memory will go away after the end of a transaction. So you don't use it to store anything permanently. It's simply a long byte array. So if you know Rust, you can think of it as a vec of U8s, where each byte is just an item in the vector, or a hex string if you're more familiar with like Python or whatever. And internally, Solidity in the EVM uses this for things like return data, reverts, strings, recursive-length prefix, etc. I'll talk about some of this more later. Now, if you actually want to persist information forever in a contract, you can use storage. And it can be thought of as like a mapping or a hash map or kind of JSON in a way where you give it a slot and it points to a value. So like if you are at the 0 slot and you store the value for hello world, you'll get a storage that looks similar to this on the right. storage is used internally to store immutable variables like symbol or name, ownership information, etc. And balances, obviously, like ERC20. It's relatively simple.
Bro, amazing
Yeah,
format, man. Amazing presentation and amazing format. I mean, this is really, really high quality.
thank you. Yeah, call data is what you're actually sending to a contract when you're interacting with it. And if you look at the bottom, that's an example of a call data or of some call data you might send to a contract. In this case, it's Blur's token. And you probably have no idea what that transaction would do, but I'm going to teach you how to read it, kind of. And this call data contains all the instructions that the program needs to execute. So if you just send a contract some call data and a value, it can do whatever you want. And that's pretty much what you do every time you interact with a contract behind the scenes. So now I'll teach you how to read a bit of call data. So the first 4 bytes, this 2E, 1A, 7D, 4D, is called the selector. And pretty much what that means is if you take a function signature in like human readable terms, like withdraw uint 256, so a withdraw function with one parameter uint 256, and then you hash it with keccak 256, you get this long string. And if you notice, the first 8 bytes, or the first 4 bytes, oh shit, first 4 bytes match up with the first 4 bytes of the call data. So it's used internally as a little kind of selector thing for the EVM to say, okay, what function are they calling? Let's look at the first 4 bytes. Oh, they're calling withdraw. Let's do some code. And I'll talk more about this later. But using this knowledge, we can actually reverse and decode any arbitrary call data by using a database of these signature selector pairings. And I've linked one at the end of the talk. It's called Etherface. I know Sam CSUN also has one called I don't remember what it's called actually, but there's a lot of them out there. I just use Etherface personally for Heimdall because it's huge. It has a couple million selectors. And with this information, you can actually give it any transaction hash, and without having the ABI, you can decode any of these
So how do you keep
calls.
the list
So
updated? Do you have a repository or something?
I don't manage Etherface, but I know that they have a scraper running. So whenever you like make a new GitHub repo with Solidity code in it, the scraper will find the ABI and then upload the signatures.
Very interesting.
Um, it's open source, so if you want to take a look at how the scraper works, you can. So I think that's pretty cool as well. And you can also self-host if you want to. But so this call data that we looked at before, if we put it into Heimdall's decode module, you can see it finds 2 different signature matches, withdraw and owner transfer some BS. And if you decode it, it says it's a withdraw of 32833, some integer. And this is just a withdraw of some Blur tokens. So now we're going to talk about bytecode and assembly. So the bytecode above, this is for wrapped ether, OXCO2, C02, I don't know the rest, but this is the bytecode for it. You have 60, 60, 60, 40. I'll talk more about what those mean. But if you actually disassemble this bytecode, you can also do this with Heimdall. You get a representation that looks similar to this. And you can see that 60 push 60. So you're pushing 60 onto the stack, you're pushing 40 onto the stack, and then you store it. And these are called opcodes. So the number on the left here is the program counter, which you saw earlier. And the program counter basically just tells the EVM what instruction to execute next. So you start at 1. Actually, I think it starts at 0, but mine starts at 1 because I don't know. But yeah, so you have the PC on the left, and then you have the opcode, like mnemonic name type thing. Internally, this doesn't actually exist, and these can change, but they're mostly agreed upon. People agree 60 is push 1, You're pushing 1 byte onto the stack. And I'll talk about each opcode, I think next. Yeah. But this is what bytecode looks like. This is what is stored in the EVM in the state. And then this is what we can represent it as and sort of read as humans, but we can make it look nicer. So I'm going to talk about each opcode now. Just to give you a feel for what they do. I'm going to go kind of fast for ones that seem self-explanatory. Yeah. So the first opcode is 0, stop. It just stops execution. Pretty simple. Doesn't return anything. Yeah, and then you have some arithmetic operations like add, multiply, subtract, divide, line division, modulo, sign modulo, and then some quality of life opcodes like add mod and mod, which just take in items from the stack, and then a plus b mod n. It puts this back onto the stack. So what I'm on right now is actually called EVM.codes, and it's a great resource for like working with this type of thing, like with EVM in general and assembly. So if you want to like see or like debug what you're doing with assembly in the EVM, you can just do it in here. It's pretty sick. So you can see I told it to push 42 onto the stack or OX42, push 1 onto the stack, and then store it in memory.
Can I make a question here, bro?
Yeah.
So when you look at a bytecode instruction set, so a list of, let's say, opcodes to run with the program counter, it looks to be a very simple steps of execution. So I have add, move, push and everything. But that seems really hard to understand. I know it looks simple, but it seems also really hard to understand because once you get a simple function, just a storage contract, one variable, one set function, there's a lot of opcodes there. What is the real barrier in there that we need to understand to be able to decode those in our heads,
Yeah, so I think practice makes perfect here. The more you work with opcodes, the more you're going to understand how they interact with each other. And also working in the EVM playground here, you can also get a feel for that. There are ways and heuristics you can use to convert bytecode into Solidity code, which is what Heimdall specializes in. And I can probably talk more about that later.
Awesome.
But I just want to go into what each opcode does. So
Awesome.
you have some more opcodes like exponent, and then extending some two's complements. Then you have comparison operators, less than, greater than, sign less than, sign greater than, equals is 0. Oh yeah, you can also click these to expand and like get some examples. Like if you give is 0 10, it's obviously not 0, so you get 0 out. If you give it 0, you get 1 out. Pretty simple. And then you have bitwise operations, and you shouldn't confuse these with like logical operations. So this is a bitwise AND, which just means if you like put in these two things, like OXF and OXF, you're gonna get OXF out when you might expect to get a Boolean out. It's not logical and you should keep that in mind. Most operations in the EVM are bitwise operations, because that's how computers think. So you have some bitwise operations and or XOR not. You have some helper functions like byte to get a byte in a word. If you want to get like the 4th byte of hello world, you can put in hello world as X. Say you want 4 for I, and it'll give you the 4th byte. Pretty simple. You have more bitwise operations like shifts. This one is an arithmetic shift. It's used sometimes. And then you have the Keccak 256 opcode, which is called SHA-3 some places. Some places it's called Keccak 256. Like I said, the names aren't completely always agreed upon, and sometimes they'll change. Don't worry too much about memorizing this. The more you work with them, the more you'll understand. And also, it's not important if you're just doing like Solidity. I'm just talking more about what the EVM actually works on. Then you have things for getting the address of the current account, getting a balance of an account, the origin of the transaction, caller of the transaction, call value sent to the transaction, loading call data at some certain index. So if you put in like call data 0, it'll give you the first 32 bytes of call data. Call data size is just how big is the call data, how much did they send. This is useful in a lot of ways, and I'll go into that later. Call data copy, copies call data, code size, size of the code. Pretty much self-explanatory. Gas price, price of gas. This is copying external code size, external code, copying it to memory. So you give it an address, the offset in memory where you want to store the code, and then the offset and size of the code that you're looking for. It'll copy code from another account. This is used in like, if you've heard of the store S-Store2 contract people are making, they're storing data in contracts and then use like Xcode copy to copy it into a different contract and then do something with it. And it's pretty cool because it allows you to store a lot of information for pretty cheap. So people are pretty creative with the way they use these opcodes. Return data size, people also are creative with. It's usually just returns if you make like an external call, like a static call, and you call return data size, it'll tell you the size of the return data, obviously. But people have realized in optimization challenges that you can just say return data size, and if you haven't made an external call, it'll just return 0. So before the push 0 operation existed, they used this to just push 0 onto the stack, and it was 1 byte cheaper than push 1 0. So that's pretty interesting to me. You can also copy return data into memory. You can get external addresses code hash. You can get the block hash of a block that you want. And then some more context like Coinbase, timestamp, number, difficulty became prev-random. Now it's just like a relatively pseudo-random generator. Gas limit of the transaction, the chain ID you're currently on, the balance of this account in way, the base fee for gas in way, or maybe it's G-way, not entirely sure. I forget. Pop will pop one item off the stack, so like the most recently added item will just be removed and nothing else happens. Then you have important memory operations. You should definitely know these. Mload will take in an offset and then load 32 bytes from that offset. So if you give it like, I'll go into the playground. Where's the playground? Oops, here. Yeah, so this will store 42 in memory, and then if you want to get that memory back out, you can push 1 onto the stack. And then load. And then this will push 42 back onto the stack. So if I step through it instead of just go through, we put 42 into memory, and then we tell mload that we want the first item, or we want this entire word back on the stack, and it'll put 42 back on the stack. So it's a nice way of getting memory, or getting memory back into the stack. Mstore stores memory. We saw that previously. You give it an offset and a value, and it'll store that value at that offset. This value is 32 bytes by default. Mstore8 will store a single byte at the offset. So if you just want to store 1 byte somewhere, you can use mstore8 for this. Compilers are good at doing this kind of thing, so you don't have to worry too much about the difference. It's just important to know memory operations. And then the same goes for storage. You can save a key and load a key. I'm going to also go into the play ground for these. So you can store the value 42 slot 0, and then you can also load it back into you can also load this value back into the stack. Like that. So those are storage and memory operations. Pretty important. Jump and jump I are extremely important. They allow you to do everything from loops to recursive things. And they're pretty fundamental in any virtual machine language. So this will change the program counter to whatever value you want. So if let's say you're on like the first program counter and then you want to jump to the 100th instruction, you just say jump 100, it'll jump to 100. But it's not conditional. The conditional jump is jump I, and you also give it a counter, but you also give it a variable or a value. And if this value is anything other than 0, then this jump will go through. And if this value is 0, then you just continue and you don't jump. So you can think of it sort of like an if statement in code. And actually, Heimdall, when decompiling a contract, it'll take these jump I's and assume that they're if statements, just because that's how compilers like to show if statements. PC is the program counter opcode, just returns the program counter. msize returns the size of memory. Gas gives you the rest of the gas left. Jump test is if you're jumping to a counter, a program counter, it has to land on a jump test. Otherwise, you'll probably end up breaking something. Then you have a shit ton of push instructions, like push 0 just pushes 0 onto the stack. Pretty simple. It was recently added. It didn't exist up until the last update, which was Chapella or something. Shanghai. Then you have the push operations where you push and then you tell it how many bytes you want to push. So push 1, push 2, and then you give it 1 byte, 2 bytes, 3 bytes, all the way up to 32. Then you can also duplicate values. So if you want to duplicate the first item on the stack, you use dup1. You want to duplicate the second item on the stack, you use dup2, and so on, up to 16. And if you remember back to the beginning of this talk, 16 was the stack depth, and this is the limiting factor. That these opcodes only go up to 16. You don't have like a dup 256. If you did, then we could go and fetch 256 stack items, but we don't. So that's kind of sad, and that's why you run into stack too deep.
There's any specific reasons for that, or it's just the choice for the design of the architecture?
I'm not entirely sure why they chose to do 16. I think in my world, my perfect EVM, I don't know if it'd be perfect, but in my ideal EVM, you would have a way to like say dup and then a number. So like dup space 10, and then you duplicate the 10th item on the stack.
Interesting.
Yeah, and that would allow you could like duplicate the 1000th item on the stack, and that would give you no more stack too deep errors. There's probably a lot of things I haven't thought of there, and like caveats or whatever, but who knows? So then you have swap. Swap also only goes up to 16, but you're just swapping the 2 items. So if you do swap 1, you swap the first and second item. Swap 2, you do the first and third. Swap 3, you do the first and fourth. Yeah, all the way up to 16th, first and 17th items. Then you have logs, which if you've ever seen like events emitted, like a transfer event, it's actually a log opcode under the hood. And you give a log opcode offset size in memory, and then it'll go and pull this information out of memory. So if you have like, let's say, hello world saved in memory and you want to log that for some reason because you want to waste 375 gas, you just say log 0 offset size, point that to the hello world, and it'll create a log forever on Ethereum. If you ever used events in Solidity that you call indexed, like you have an indexed event, then you're going to be using topics. Most of the time, topic 0, which is this first one for like log 1, will correspond to a kekak hash of the selector, similar to how functions work, but it's 32 bytes long. And I can probably talk more about that later if people have questions.
This is a Bloom filter
But,
too, right?
I think so. Yeah, because then you can like actually look up information with these logs, and it becomes pretty fast. It's really easy to search through the state to find logs with topics, like index topics. But a lot of people have been moving away from index topics just because they cost more gas.
I heard some people are using events in order to save gas instead of storing the information on storage, you know?
What are they using?
Events.
Yeah, so the log is the event. It's the same thing, but under the hood, it's called a log, or like the name that people have given it is log zero
But
for
there's
zero
no
topics.
storage, right? So I can just like have a log and then don't even need to use storage for that. That will cost
Yeah,
less gas in the end, right?
yeah. So people instead of like logging topics, like I think Seaport will log zero, and then they just give it all the information is stored in memory. They use log zero, costs 375 gas plus or minus, not just plus some for how much they're logging. And they can kind of log an obscene amount of information for relatively cheap.
I have a question here. So where logs are stored?
They're stored in the state Merkle tree.
Awesome.
Yeah. I haven't talked much about that because it's something I don't completely understand myself. I'm still learning. But basically, the Merkle tree, like the state Merkle tree, has all the information for account balances, um, contract code, storage, logs, etc., in a really easy way where each Merkle root can be verified um, and proven. So it's a very efficient way and kind of an ingenious way that Ethereum uses to store information in a way that can be validated. Um, so yeah, those are the log opcodes. The number here just corresponds to the amount of topics, and they all work the same. You can only log up to 4 index topics, which is why you can only do 4 in Solidity because of the EVM limitations. We're almost done, so yeah. This create opcode creates an account. You give it some value to send to the account, and then the offset and size in memory. So you store the code for the account in memory, and then you call create, point at memory, and it'll create a new contract with the code, and then return the address back onto the stack. And then you have different call functions. Um, this one, call, is just a message call into an account. Call code is a message call into an account with an alternative account's code. So you can pretty much emulate another contract, kind of, which is how proxies work, but they use delegate call. And then return takes in a part of memory, like an offset and a size, and then we'll return that data and halt execution. Delegate call is the same as call code, message into a call, or message into this account with an alternative account's code, persisting values for message and send, or for sender in the value. So this is used in like proxy contracts, so that the proxy contract can have its own state that persists, but then the contract is still upgradable. Um, then you have the create to, which is the same as create, but it takes in some salt, which is why people use this one so that they can like mine vanity addresses. Like if you look at the Seaport address, it has like 20 zeros before it or something. Probably not 20, but like 10. It has like 10 zeros, and it just makes it a tiny bit cheaper for people to interact with the contract. So they write things where they can crunch this number and
Isn't
get
that
a more.
dangerous? I mean, I heard that every time you have one of these addresses, I don't know, so people are
Yeah,
mining it all the time.
yeah, so there's no like you if you have an address that you want to mine and like you want to impersonate the zero address, you can't do that just because it gets impossible. But if you want to get like an address with like 10 zeros before it, you can do that within like a day if you're just running it on your
I
laptop maybe.
understand.
Actually, Probably not a day. It might take you a lot longer, but you can get quite a few zeros for a vanity address.
And there's also the
And if you look,
situation that, this is not a EOA, right? It's just a smart contract, so there's no way of impersonating it.
yeah, it's just a smart contract. And then recently there was a random number generator like exploit for one of the things that was generating vanity addresses, and that was kind of bad. People had their wallets drained.
Yeah.
It can be pretty cool to have like Beef Babe as your Ethereum address. Like mine is just 6 6s and then some other numbers I forgot. But yeah, and then static call is another message call into an account, just normal. Revert is like if you've ever made a transaction and it reverted for whatever reason. It's similar to return, takes in the memory and then returns it or reverts with it. And that just halts execution, reverts every state change. So like if you stored something in storage and then reverted later, that storage doesn't exist anymore. It's been erased. Um yeah. And then the invalid opcode just consumes all the gas and then halts execution because you're out of gas. So don't use invalid opcodes. It's great. And then self-destruct will stop execution and then the account will be deleted. So you have to give it an address to send any funds to, but this is how you can lock funds. So be careful with this. So now that we've gone over every opcode and you probably don't remember any of them, we go back to the presentation. So now we're going to talk about program execution. You probably saw that earlier. Don't worry, I'm going to explain what this is and it's going to be great. So I'm actually going to unminimize this because I'm going to have to show you some things. But let's take the wrapped ether contract address, and we can ask Heimdall to generate the control flow graph for it,
Bro,
which I've already done before.
I don't know if you can do this, but if you can make your font a little bit bigger whenever you're dealing
Yeah,
with code, okay? Thank you.
I'll zoom in, yeah. Um, so this entire thing, this like big tree structure, is the entire execution that a contract can take. And you can generate this using Heimdall. There's other generators out there. But basically, it takes assembly that you saw earlier to a new level, and it allows you to visualize the assembly. And we're going to talk about that. So we're going to start here at the first operation. We're going to push 60 or OX60 onto the stack, push OX40 onto the stack, and store it in memory. In Solidity, this is a Solidity contract. So in Solidity, they use they use a free memory pointer, which is basically, you can think of it as just like, let's save some space for later for memory operations. So this is what that does. These first three instructions just create that memory for Solidity to use later. Then we're going to push 4 onto the stack. Check call data size. And if call data size is less than 4, we're going to jump somewhere. And where are we going to jump? All the way down here. We jump here, which is the fallback function. If you've ever used Solidity, if you try to call something and that call doesn't exist, you can go to a fallback function. So in wrapped ether, this is the fallback. I'm not going to go into code every single one of these things because that would take me all day. But this is a deposit fallback function. Yeah, so if you send wrapped ether like 1 ether and you don't call anything, you'll still get your 1 ether deposit back, which is kind of nice. And that's because it's checking the call value for the 4 bytes that you send at the beginning. And if you don't send anything, we go to the fallback. Well, let's say you do send something. Then you go to this block and you jump to here. You jump to instruction OXOE. Or no, you don't jump. So if the jump was not taken, then you go here. Yeah. So then you push 0 onto the stack. This contract was deployed before push 0 existed, so they do push 1 0. But it's the same thing. Push 0 onto the stack, load the first 32 bytes of call data, and then do some arithmetic to shorten the call data, blah, 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 perform an AND mask. Yeah, so I'm not going to assume you know how to read this, so we're going to go and dump it into this, the playground, because that makes it easier to visualize what we're doing. So if we take this first code, where do we want to go? Let's go up until OXB9. B9, jump by. Paste this into the EVM playground. You'll see all these, get rid of this. All these opcodes correspond to what you see here. So we can actually start, let's give it some, if we don't give it call data, you'll see it'll revert because we didn't give it the fallback function path all the way down here. We didn't copy this part of the code, so it'll just error out. So let's give it some call data and see what's happening. So if we give it OX6969696970, just to show the AND mask working, and we run this, step through, free memory pointer. How do I want to clear this storage, but it doesn't matter for now. So this storage doesn't exist. This is from the previous thing. Just ignore that. So we free the memory pointer. So this is internally Solidity doing it. Push 4 onto the stack. Push the call data size onto the stack. Since we gave it 5 bytes of call data, 5 is not less than 4, so we get 0. Now we're going to push this jump I. Since the jump I is 0, we're not going to jump, and we're just going to continue. So now we've went from this block to this block. So now we're going to load the first word from call data. So you can see it loads all of this into the stack, and then it adds all the zeros at the end, because every word on the EVM is 32 bytes, if you remember. So then we don't want all this because this number is a lot different than this number. It's a huge difference if you convert hex to int. So we're going to divide and just get the first 4 bytes. And then we'll perform an AND mask, which I'll talk about a bit later. And that just gives you the same output. FF 8 times, or F 8 times, FF whatever. This just makes it so that if we gave it, how do I explain this? It's just a bitwise AND mask, so it'll take only the first 4 bytes of whatever you give it. And since we did this division, it's kind of not needed, but it's still nice to have. And I'll talk more about AND masks later. But yeah, so now we have our function selector on the stack. We're going to check if it's equal to this function selector. First, we duplicate it so that we don't just lose it and have to do all this stuff again. But then we push this function selector on the stack, check if it's equal, give it the place to jump to, and jump. Since they're not equal, we're not going to jump. And I didn't copy anything else, so execution ends. But these first 2 blocks here, I like to call the function dispatcher. Actually, it goes on a bit longer, where so this OX06 FFD, it actually is a function selector. So if we go to Etherface and we paste it in, it's actually the name function. So if I explain what this is doing in a higher level term, it's basically checking the first 4 bytes of the call data against every selector in the contract. So if I did give it this OX6FDDE03, the name selector, it would jump me to this name function right here. And then it would form the name function and return the name of the smart contract. But since it didn't match, we move on to the next selector, which I think is transfer. I could be wrong again, but if we're doing a transfer, we jump to the transfer block. And then if we're doing whatever this is, we jump to that block. And it basically all the smart contracts work in the same way, where you have a list of these selectors that you want to check for, and you just keep checking, like, is the first 4 bytes of this call data matching a selector? If it does, we're going to jump to that function and continue with the execution. So I call this the function dispatcher, and it actually allows you to like Heimdall can detect the 11 selectors in the wrapped ether contract just by following this kind of pattern. And it sees like, okay, this is a function selector because we're comparing it to the first 4 bytes. This is a function selector. And then we can use that information to build the ABI without having any knowledge of the actual contract itself or the actual validity code. So that's a bit about program execution. You start at the first block. We're checking call data, checking for function signatures, and then jumping to the block of code, block of assembly that represents Solidity. Now we're going to talk about how Solidity EVM represent types. So I was trying to explain and bitwise masking earlier. But basically, it just allows for the EVM to include a subset of bits from the whole word. So I'm going to go to the playground so I can explain this better. I want to be in byte, or I want to be mnemonics. So if I go over here, let's just say we push this onto the stack. I think that's 8. We push 8. Push this onto the stack. If we just want the first 4 bytes, we can push 4 and then run that. Or not. Maybe I have them backwards. Okay, well, I don't know what I did. But basically, if you want the first 4 bytes here, then you would AND it with OXFF. So you would have 4 bytes of just Fs, and that'll give you the first 4 bytes here. If you wanted the second 4 bytes, you could do this, and it'll give you these bytes instead. And it's just a way that Ethereum EVM uses to cut types down. So if we go to wrapped ether, I saw in the fallback function down here, like I can just tell types just by looking at these masks. So if you remember back to the opcodes, caller returns an address, and then we're pushing 20 Fs or 20 bytes worth of Fs onto the stack and then AND masking it. So anytime we see this 20 bytes of Fs, we can just assume that the variable it's masking is an address because addresses are 20 bytes long. So hopefully that makes a bit of sense. But this is how Solidity drops off bad data and sanitizes its variables to make sure that it's only working with what it's looking for. So in this case, it's looking for the caller, and it wants the variable as an address. So we're going to cut it down with an AND. And I never realized this, but they actually do it twice. And I think this entire second part can just be cut out. So we need an optimizer to talk to wrapped ether. If we go back, how can we tell the difference between types within the EVM? I kind of just showed it. If a bitwise operation other than a mask is performed on a word, it's likely a bytes type. So like if we go to the EVM codes and we look at byte, like if we're calling byte on something, it's probably a bytes type because we're extracting a single byte from that variable. And these aren't facts. These are heuristics that I found in my time from reversing bytecodes. But like if we're calling XOR, that's not an arithmetic operation. I don't know why you would ever do that on a non-integer. or on an integer and not want it. So if you're doing these operations like XOR, byte, sometimes shifts, then I assume they're bytes types. If you're doing arithmetic operations like this arithmetic shift or add, multiply, divide, mod, all those. Actually not mod because that's technically not always arithmetic. It could be cryptographic. But if you're doing like multiplication with two things from the stack, two words from the stack, it's probably a uint or another number type like integer. And then strings, dynamic types, arrays, etc., are stored in memory because they're typically a lot longer than 32 bytes, and you can't fit those on the stack. And they're typically encoded in RLP format, which is recursive-length prefix. I'll talk a tiny bit about that on the next slide, but it's a really complicated like protocol thing, and if you want to learn more about it, you can read about it on ethereum.org. They have a nice blog that details what it is, how it works. And then how does the EVM represent mapping? So if you've done Solidity, you kind of type something like this. You have a mapping from one type to another type, and then you have the variable name. So under the hood, this is represented as, well, first, to get the key of this, like if you're putting in this key, the bytes 32 key, then that becomes this first 32 bytes. So let's say we're putting in the key 1. It's just going to be zeros until you get to 1. And then we're also going to concatenate the mapping slot. So let's assume this is the first mapping we've ever added. It's going to be zeros. And then we go back. We get the hash of this entire thing. So SHA-3 in memory. I'm going to assume the memory is just whatever. So we pass this into SHA-3. We get some random hash output that's 32 bytes long out. And then we store the value at that slot. And this is great because it ensures that there's no collisions with either the key or the slot. So like these two mappings have different, even though they're the same types, they have different internal hash. So like this first one would be this number. The second one, I don't know if I can copy this. I can't. But the first mapping, this mapping, would be this hashed and then store it. The second mapping would be this, except instead of the 0 at the end, it would be a 1. And then you hash and store. And since hash functions are like one-way and deterministic, and there's a very tiny chance of collision, this is a very efficient way to store information. And this is actually the way that all the contracts use to store information, like NFT owners, balances, approvals, etc. And it's pretty efficient at what it does. Then RLP, again, I'm not going to go into depth here because it's kind of complicated and not fun. But it's just a way of encoding data in Ethereum, and is primarily used for serializing and deserializing data in memory. So it's pretty complex. Like this is the actual like outline of how Ethereum does it exactly. Like you can see the string dog is this monstrosity. You first push this byte and then you have all these individual bytes. There's a lot of rules to it. So if you want to read this on your own, go for it. I'm not going to talk about it right now. It just, all you have to know is that the EVM uses RLP to store pretty much everything. They store lists in RLP, strings, arrays, other data types, because the EVM can understand these, and all the operations that the EVM has can easily do RLP decoding and encoding. Yeah, it basically involves just prefixing the data with the length of the data so that it can be indexed pretty quick. And that's that's all for RLP. I don't want to go too in depth with it because it's a lot. Yeah, so I think I'll share these slides later. Just go and read this if you want to learn more about it. So now we're on to the helpful tools and resources. Heimdall. I'll show you the decompilation thing because I know that you asked a question about it. But Heimdall is an EVM toolkit for reversing, decompiling, decoding, Calldata, viewing contract storage, and more. It's really great for working with unverified contracts. You don't have to have the source code or the ABI to work with them. EVM codes we've been using this whole time. It has this entire opcode directory where each opcode has examples with edge cases. And you can click to expand. You have the playground here. They have precompiles here. It's one of the best EVM resources out there, and you should definitely be using it if you plan on learning the EVM. Foundry is obviously cutting edge toolkit for working with smart contracts, the EVM, and more. You can use things like cast in Foundry to send raw transactions. That's pretty useful as well. Ethereum.org has great resources for reading more about the EVM, like obviously RLP. I think I linked one earlier, but they also had that graphic on the first slide. They have pretty much any question you have about the EVM can be answered here. Etherface is this signature database here that we used earlier to find out that that was actually name. So yeah, if you're trying to reverse Calldata and you don't want to use Heimdall, then you can just like type in a hash here, and you can also do text search. Balance of. This is the signature for it. It's a very useful tool for reversing EVM Calldata. And then REVM is a Rust-based implementation of the EVM. If you want to read the source code for it, it's great for obtaining a deep understanding of the internals of the EVM and all the caveats and stuff. I would recommend reading REVM's code over Heimdall's VM code because Heimdall's VM is an EVM that's it specializes in symbolic execution. Like if you look at the stack implementation, it doesn't just store the value on the stack. It has a lot of other things that you don't really need to worry about. And before we finish, I'm gonna go back to what you asked about earlier, and I will show you how we can actually decompile a contract. So if we like, since assembly is really hard to read, and it's hard to understand what's happening in your head when you're reading assembly, what you can actually do is just decompile a contract using Heimdall. And this takes all the knowledge that I have about the EVM and compiles it in a way where you can just run this command and it will start to do all this heuristic type stuff.
Awesome.
What's up?
Awesome.
Yeah. So it first like finds every single possible selector in the symbolic execution and then executes them. It'll handle resolving all the signatures for you, all the events for you in plain text. So instead of you getting like a hash, you get all these nice little human readable outputs, which is great. So like you can see name is that OX6FDDE03. Nobody knows what this is, but you can see that it's the name function. And then what's great is that you can actually, it'll output a Solidity-like file. I have to redo this. Got some flags. So if you tell it to include Solidity, I don't know if that worked. Did it? Yeah, so it'll output an ABI, and this ABI can be called, so you can see like the entire contract ABI is here, and it does that working solely off the bytecode. So this is what it's working on. It just takes this massive string and crunches it down into this ABI, and it also outputs Solidity code you can read, kind of. I think it's a lot easier to read this format than assembly. Hopefully you agree with me. I don't know why. Oh, I made it change.
I know a lot of people are doing it, so I bet it is,
Yeah. So like you can see name is returning a string from RLP encoding the first storage slot. So wrapped ether actually stores their name in storage, which is kind of silly because they could just hard code it. It's not changing anytime soon, but that's just how the EVM works. You can see total supply is actually just returning the balance of the contract. Symbol is returning a storage value, RLP encoded. Deposit takes in the message sender and then stores it in a mapping and then emits deposit event. So like you can use Heimdall to just process all this information that you have and distill it down to a readable format. And if you want to read YOL instead, you can. I don't recommend it because this is not fun and it's probably easier to read assembly, maybe, but it's an option for you. You can also generate the control flow graph with Heimdall.
Very
It can do a
interesting.
lot.
Yeah,
Yeah.
yeah. Seems like a pretty good tool. I don't know.
Yep.
David, do you have questions?
Yep. Feel free to ask questions. That's all I have for now. Yeah.
Amazing, amazing presentation. High quality. This will be a huge
Yes.
success, bro. Thank you so much.
Thank you.
Yes, hi. Very interesting presentation indeed. Thanks a lot. I have a question I asked in the chat about self-destruct. I thought it was being deprecated. Do you know something about that? I have not. Maybe
Yeah,
I
they've
can
been
prove.
deprecated, right?
They might be planning on it, but I don't think it's been created
I
right
will
now.
keep a link. Yeah.
Has it?
Yeah, I think you don't have self-destruct on Solidity anymore, but you do have it as an opcode on assembly.
Okay, that makes sense. Yeah. Okay. I did not know that. That's pretty interesting. I actually don't know how to see chat.
There's a
Is it?
yeah, it's a little bit tricky. The UI on Discord for that is terrible. But if you see the user room on the meeting itself, there's a small box. But that's the I only have one more question in the chat here, which is the jump I destination block of the function hard coded in the compiling process when compiling the code from Solidity to bytecode?
Yeah, I see it now. Yeah, so all the jump instructions are decided by the compiler, so you don't have to worry about that. If we go back to the control flow graph view, you can see like this will never change. It's always going to jump to OXB9 as its next instruction. And you can see it'll here, and the jump test is here. So these jump test opcodes, it has to jump to one of them. If it doesn't, I think execution reverts, or it might just crash. I'm not entirely sure. But I know the compiler will freak out if you try to do something weird. So these always have to be hard coded. If you're writing raw assembly, you can do something called like a dynamic jump, which actually was in a CURTA contract. So like, nope, nope. Okay, think about. Like if you push something onto the stack, like actually, let's say you're loading push one. So we're loading the 32 or the first word from Calldata, so offset 32. And then let's say that's a jump instruction. And we actually want to jump to this value in Calldata. Let's say push 0. And we want to jump to program counter 100. If you run this, it'll try to jump to program counter 100. What? Oh. Okay, it'll try to jump to this program counter OX10. But it doesn't exist. Actually, not OX10. That huge number. But yeah, so these are called dynamic jumps, and they make symbolic execution really hard. The good news is Solidity's compiler doesn't do it by default. I don't think Viper's does either. So the only time you're going to run into these is going to be like someone's trying to make it so you can't reverse their contract. Yeah.
So I think Luke Hook has a question.
Go for it.
Amazing, bro. Thank you for the presentation. But I just have some confusion about, for example, when you write Solidity smart contracts, then you compile it. So the first thing, we have some block of functions that are separate in chunks. Like I think, I don't know, correct me, please. Then we have the first thing of execution. We have all the function selectors. It's gonna loop about all these function selectors. Then when it match, for example, with one function selector, it jumps to this chunk where the exact block of this function and execute the rest of code. Am I right, or?
Yeah, that's right. So you start when you compile a contract, it compiles to this big code that no one can read, and then you can disassemble it to see this, but also you can't read this. So the control flow graph is completely right. You start at the top, and then you're checking the selectors. If the selector matches, you jump to that function body like this. So yeah, you're completely right.
Question. Thank you again. Thank you.
Does anyone
Awesome.
else?
I think this is it. You have anything else to add?
I don't
I
think.
have one complementary question on my self-destruct, if you have some time still.
Yeah, go for it.
Yeah. So if a contract doesn't implement self-destruct, I'm thinking of a NRC 4626 volt. Is there a way to stop the possibility to deposit into this vault, or is it just not possible?
Is it after you self-destruct, you can't deposit to it?
No, I have a vault, an ORC 4626 that is deployed, but there is no self-destruct function in it.
Yeah, a lot of contracts don't implement self-destruct just because it's very dangerous.
Yeah.
A lot of the time, it's just like bots or exploit contracts will. But you're not going to see it in the wild a lot. Like very few contracts use it just because it's so volatile and it does destroy things and break things, which is why it's been depreciated or whatever. So yeah, you're not going to run into it too often.
Yeah, but my question is, I want to, the MRC 4626 is for generating yield, and I have deployed such a contract, and I want people to stop depositing this contract using the deposit function. Do you know somewhere? Or I don't think it's possible, but I don't. I just wonder.
That you want people to stop being able to deposit?
Yes.
I think if you self-destruct, they can't anymore. No, they can. Because you can send Ether to any contract address, and it'll just be lost there forever. If you want to stop people from depositing, you can add like a flag, like in storage, like store a flag, and if the flag is true and it's like deposits paused, and if the deposits are paused, then you just revert, and that'll stop them from sending money. It'll send the money back to their account. So I don't think, yeah, you wouldn't use self-destruct for that. You would use revert.
Yeah.
Hello?
Hey.
Can you still hear me?
Yeah, I think you dropped for a second there.
Yeah, I think my internet